So we're starting with session one, and I want to welcome everyone. This is kind of exciting for me. It's been a learning adventure for me, and hopefully it'll be a exciting one and a useful one. That's mostly what I've tried to do with this for every one of you out there on the call. So you are all on mute except for Darlene. And Darlene's here on the call with me. She's volunteered to be the first cohort rep on this call. And basically her job is to sort of be a proxy for all of you and to help me clarify and to ask questions and to just sort of attend and keep me on track and to dialogue with me so that you don't have to hear my whole voice for this whole session. So the way this works is I sent you the PowerPoint slide deck, and so we're going to go through it, and as we go through it, I'm assuming that you'll be looking at your deck while I'm looking at mine, and I put numbers on each of the slides, and I will announce when I'm switching to a new slide. I'll announce the number, but I won't be announcing the animations between slides. I'm just going to assume that you'll be able to follow along with what I'm saying with what's on the slide. I also want you to know this is going to be my full-time job for the next 6 months. You know, delivering and working with all of you on this training. So because that's the case, between sessions, I'm available for office hours. Anything that people want to ask, you know, any questions, any situations. If you want to email me, I'll totally respond. If you want to make an appointment and just have a telephone conversation about stuff that we cover in these sessions, I'm more than willing and happy to do this because I think this material is really important. I've probably been a spiritual seeker, a psychological seeker for 50 years. And social neuroscience for me has been an evolution and a revelation in terms of helping me understand both my own personal journey and all the other people in my life. You know, it provides a framework that really helps me make sense of stuff that previously I couldn't make sense of. Right? Does that make sense, Darlene?
That does make sense.
Yeah. Okay, so you should be looking at slide 1, Brain Basics for Learning Lovers, and it's a picture of a person who looks older than me, actually, with the inside of his brain exposed. And we'll be alternating, giving equal time to the genders. So session 2 will be a woman's brain exposed for all of us to take a look at. So let's move to slide 2, if we can. Slide 2 is a picture of me. I thought about having live video, and I've tried live video before, and mostly what I discover is it serves as a distraction. You know, people spend more time looking at me than really engaging with the material. And so for that reason, I'm just going to provide you with this still. And if we click through on slide 2, you'll see a close-up. This is me with wood chips all over from cutting down a dead tree. And then I put a few, 5 brief things about me. If you keep clicking, you'll discover. So in addition to the doctoral degree, I have 2 master's degrees. One in family systems, because at one time I was interested in being a family therapist, and another in general counseling psychology. And then my PhD is actually in something called transpersonal psychology, which is supposed to be a psychology that explores the pinnacle of human development. Although my experience with that is mixed, to say the least. Another thing about me that I put on this five brief things slide, is that, and this is something I'm really proud of, and that is, together with friends, I started a grief counseling program for children who suffer serious loss. This was at Cara in Palo Alto. And I stayed involved with that program for 20 years. And that program informed a tremendous amount of what I'll be presenting over these next 12 sessions. More than I even realized until I actually got into the material itself. Next thing about me is I've been doing self-funded postdoctoral study in neuroscience for the last 10 years. And the way I actually came to do that is, so for 10 or 12 years, I spent at the Institute for Transpersonal Psychology, which was sort of like just to generalize, it's kind of like a right brain woo-woo school. And then I spent 10 years at a think tank at Stanford just on intuition alone, thinking this would be kind of interesting to take this job. And so a maintenance man with a PhD, this is a really exclusive place that you have to have a PhD to be the maintenance man. That was the joke that we had there. But what it did is it gave me access to some of the leading researchers and scientists in the world. And I was able, they come there for a year, a sabbatical year, to write up their most recent research. And I got to spend 10 years there, just hanging out, seeing them up close. I think of it as 10 years doing cultural anthropology, looking at the academic in its natural habitat. And I learned a tremendous amount. And so,
can you tell some of the people that you worked with, or that you were part of their research?
I'm not great with names, but Steve Levitt, who wrote the economics book, the real popular one, I forget the name of it now. Kay Anders Erickson, who's right now is doing a study on Nobel Prize winners, who's responsible for the 10,000 hours of practice to become an expert law, right? Dan Siegel's been up there. Mm-hmm. A lot of people, Deborah Gordon, who's like one of the world's premier authorities on ant culture, she was really interesting. The woman who's the world leading expert on dolphin communication was up there. Lots of people. Don Lamb.
Was he there?
No, Peter was never there, but I invited Steve Porges to come and spend a sabbatical year there, and he was about ready to, but he had conflicts in his schedule. But it was just a really rich environment for learning, right? Mm-hmm. And then the last thing on this introductory page is, for 25 years I was a house builder, which turns out to be a really, again, and this is all intuitive on my part, it turns out to be a really important piece for keeping me sane and healthy. So, that said, that introduction out of the way, my wife and I live up here on Whidbey Island, and she's a photographer, and I continue to do my interest in social neuroscience, giving talks and presentations around the island. And let's see, this February, a friend and I will be doing a weekend presentation at Bastyr University entitled Narrative Medicine, which is a new field that we're interested in exploring. The first program was piloted at Columbia University, and it's a required course for all medical doctors right now. And basically it has to do with how important it is to hear patients, to hear their story, and to hear it in a certain way that helps facilitate the healing process, right? All right, moving right along. So we're going to go to slide 3. What is social neuroscience? Darlene, what is social neuroscience? This is a test.
Oh my gosh! Well, it feels like I live it every day.
Right, you do actually.
With 7th and 8th graders.
Right. Let me introduce you a little more. Okay, let me introduce you a little more here. So Darlene's just a few years ago received her PhD, and she's a school counselor with 7th and 8th graders.
Mm-hmm.
I would let you do the introduction, but you won't tell them all the great things about yourself, so we'll have to leave that to me. So one of the things that Darlene is, she's the lead singer in the Mojave Moon Band, and she has an extraordinary voice.
Oh, thank you.
Well, and then the other thing, and her voice and her musical abilities are only surpassed by her quilting ability. She has made some of the most astonishing prize-winning quilts I've ever seen. And she made one. I first met her as a student in graduate school as part of a cohort, and she made a quilt out of squares provided by all of us cohort members. And it was just astonishing. And it's still hanging there, right?
And it's so nice to go to ITP when you go to ITP and you see and it's all of the people that started with us. And although not all of them finished, it always feels like we're just still hanging together.
Right. It's a great metaphor. Really, really nice. All right. So what is social neuroscience? And I'm not going to read these things as we go through them, but you have the slides, and you're welcome to go through them. So basically, it was started through a little bulletin published quarterly between 1988 and 1994. And it's been around for a while, but it hasn't been known very widely. And this happens a lot in science, too often, in fact. And that is really important research gets discovered and doesn't get disseminated for decades, right? And we'll see some of that when we go through this program. That really important research findings that will profoundly impact the culture never make it out of a research lab. So part of what I'm intending here and doing here is to try to get this material out into the world more widely spread, because it's really useful and important. So Cacioppo and Bernstein, here's pictures of them on this slide, Gary and John. And for our purposes, our definition is going to be a really simple one. How the brain affects human relationships and how human relationships and the environment affect the brain. And they affect the brain in ways that we can't even begin to imagine. Next slide, 4. So these sessions are going to be structured pretty similarly, and that is, I've tried to put myself in your position and imagine what questions you might want to have answered, as a participant. And I haven't come up with all the best questions by far, and I don't expect to. And so I'm going to ask each of you on this call to feel free to come up with your own question, either now for this session, but ideally in advance of future sessions. So that will give me time to do any research I might need to do, and then to be able to answer them. Because I want this information to be useful and pertinent to you in your life, right? My 10 questions come out of me and my experience and what I imagine could be useful to you, right? Mm-hmm. Well, there's this thing that some of you out there I know about. It's called the curse of knowledge. And basically what the curse of knowledge means is that as you get more and more learned in a field, you forget what it's like to be a beginner. You forget the simple stuff, right? So I was talking to a cardiologist one day, and he was talking to me about myocytes, right? Like, everyone knows what myocytes are. Well, I didn't know what a myocyte was. And so everything he was telling me didn't make any sense. It's interesting because we were talking about, what I was asking about is this piece of research I saw that said that 60% of the heart's cells are neurons. I thought, wow, that's a lot of neurons for the heart to have. I thought neurons were just in the brain. And so I asked this cardiologist. He said, no, the heart's, almost all made up of muscle cells, myocytes. And he said there are neurons in the heart, but there's basically only about 20,000 of them, and they all have specific functions. And if you had more than that, it would actually cause problems. So that's just an aside. But so it's really interesting. The curse of knowledge. So I need help. And Darlene, this is part of your job to help me overcome the curse during this session. So here's the 10 questions. And so this is just an introductory piece on the brain. And I'm not going to be spending a lot of time asking you to think deeply and memorize all the different brain parts and stuff, because I can guarantee you by the end of these sessions, you will know the parts, at least the parts that are important for social neuroscience and that are important for your own brain workings, right? So here are this session's 10 questions. And basically each slide is intended to bring some kind of answer to these questions. The first is, what are the different, well, actually I won't read them all. We'll just read them at the top of each slide. So if you go through, I thought these were kind of the questions I would want to know, if I was signed up for this offering. Are these questions do you want to know, Darlene?
I do. I'd also like to know if there's a difference between male and female brains and how they work.
Right.
That TED Talk that shows the different ways that a man's brain works versus a woman's. That would be interesting to know.
Yeah, well, that's a whole session, actually. I forget what number it is. I think it's number 7 or 6 or 7. Yeah, there are significant differences, and they profoundly impact, especially under stress, the way we're able to relate to each other. Okay, so now we're on slide 5, different brain parts. So for our purposes, it's really not that important to memorize, as I said just a moment ago, all the different brain parts. It's mostly important to know that there are brain parts, right? And the reason that the parts came into being is because they all have a specific function, right? And they all have a specific function, and they're located where they're located because the function that they have is connected to the parts of our sensory world and our sensory organs that register experience. So, for example, we see the primary visual cortex, number 17 in this slide. The primary visual cortex has long threaded axons, which are nerve cell tails, that run from the back of the eye to this part of the brain. So it's like a superhighway that goes from your eye to this area at the back of the brain. And that's how this ended up becoming the visual cortex, right? So above the primary visual cortex, you'll see Wernicke's area, outlined by dashes inside the brain, actually, and it's partly responsible for language. And what's interesting about, and we will actually talk about Broca's area and Wernicke's area, is they're on the left side of the brain. And because of their location on the left side of the brain, some interesting functional consequences result. And we'll be talking about those, I think, next session, actually, when we do pre and perinatal neuroscience. So then the next slide shows the interior of the brain, structures on the interior of the brain. And again, we don't need to know the specific pieces because we'll be encountering them over and over again. But I'll just tell you a little bit, like, for example, corpus callosum connects the two hemispheres, that beige structure in the middle. We're actually looking at a cutaway view, so that would actually move horizontal through the brain. The amygdala is a part of the emotional processing part of the brain. And the hippocampus is responsible for memory. And the thalamus and the hypothalamus are part of the grand central station of the brain, where information comes in and then gets distributed throughout. But there is a part in this depiction here that I do want to mention, and I've mentioned in my blog several times, and this is a pretty recent discovery. It was discovered by a woman in Argentina, and that is the cerebellum. What she did was she performed this experiment to actually count the number of brain cells in a brain, number of neurons. And previous to her research, we'd thought there was roughly 100 billion brain cells. 100 billion is a really big number, right?
Yeah.
Well, she did a count, and what she did is she made what she self-describes as a brain bisque, right? She boiled brains from people who'd recently died. They were 5 men. And then what she did is she got this solution that retained the process she used is something she developed called isotonic fractionation, which is an interesting process. But basically, it was able to reduce the cells into a consistency of a liquid that didn't destroy them. And then she simply took a small sample and did a manual count. And then she extrapolated to the total volume of her brain bisque and came up with a number called 86 billion. So I wrote a blog sometime last year, I think, talking about how we overnight lost 14% of our neural capacity. Where did it go? Well, that was interesting that she developed this process, right? But here's what I found really interesting. And this is a game changer from my perspective. And we'll see why as we go through the future sessions. It turns out that of those 86 billion neurons in the brain, 69 billion of them are contained in that little structure, densely packed into that little structure called the cerebellum, right? So that's like 80% of the neurons in the brain are contained in the cerebellum. Well, if that's the case, then it would make sense that whatever the cerebellum actually is responsible for, the brain thinks is really important, right? You would think it's important, right, Darlene? If you were devoting that much real estate.
Right. Right. Yeah, and it's interesting where it is too, in the back of the brain.
Yeah, protected actually.
Yeah.
For the most part. I mean, if you're playing sports, it's rare that you're going to take a hit to the cerebellum.
Right.
Right. Okay, so now
mostly to the front of the head. Yeah. I always wince when I see soccer players bumping that ball up in the air with their
right.
heads and
we're only now discovering, like decades later, the unfortunate impact that all those head hits really does take its toll on neural functioning. So
I do have a question with the slide before that where it showed all of the different areas of the brain and what their function is.
Yeah.
And being a 7th or 8th grader, my question would be, how do you know that? How did they find that out? What did they do to know that this area was this and this area was that?
Basically, they dissected dead brains, right? So everything we know about brains, interestingly, until about maybe 25 years ago, we learned from looking at animal brains and dead brains, because we have a ethical concern and consideration about operating and experimenting on live human brains, right?
Mm-hmm.
And so you see those numbers on that diagram. Well, a neuroscientist, I forget his name right now, but basically he decided that when he did a dissection of a brain, he noticed that certain areas were clearly differentiated and demarked from other areas. And he began to do trace the neural fibers to see, like, let's say, where can we look here? The prefrontal cortex, right? We'll trace the fibers from the prefrontal cortex, and we'll see, wow, they connect to a whole bunch of different areas, but mostly they connect through this place called the anterior cingulate on the interior, and they go and they make connections to all of the emotional structures and all the fear structures, the amygdala and those structures, memory structures. And so the way they decided how to, Corbinian Brodmann is his name, the person who numbered these. And so these are Brodmann numbers, right? And so to help neuroscientists identify and know that they were all in their research talking about the same areas, he put numbers on them, right? So that if you're talking about area 45 and 44, you're talking about Broca's area, and you know that that's involved with speech and language. And so if someone has a stroke and they can't speak, well, you have a pretty good idea of where that stroke has occurred in the brain based on the difficulty that people end up with. Okay, so let's move right along here. So we're going to go to slide 6. There's an artist representation of a neuron, right? A brain cell. And that link, so on these slides, there'll be a number of hyperlinks. So hyperlink is one I already sent you folks and asked you to watch. It was that 4-minute video of an action potential. And on this slide, this artist representation, you're seeing action potentials in those white light pieces in the cell arms sprouting off of the center of the cell, right? So an action potential is responsible for everything that happens in the social world. Everything that people do they do as a consequence of their brain opening ion channels, exchanging sodium and potassium and other kinds of calcium and other kinds of neurotransmitters, and carrying an electrical signal from one cell to another to another. And that's the whole operation. And you can see that operation, you can see it in the world, and we'll identify places where it's working well. And you can see it in your life, and I can see it in my life, when it's working well and when it's not working well. And then when I notice it's not working well, I can take steps to improve brain function. And we'll go through what a number of those steps we can take actually are. And they can be dramatic, actually. I mean, I've had experiences where I could feel brain cells connecting in my skull and just firing and just energizing my whole system. So if you click again, you'll see 3 different cells. And these are basic. There's probably, so far, we've discovered close to 100 different type of neurons in the brain, but these are the basic types. And so this is all, I never majored in biology or neurophysiology, and this is all new learning for me. So essentially, motor neurons send information from the brain to the muscles and organs in the body, and other neurons in the body, right? And they do it through those long tails called axons. So when you hit your funny bone in your elbow, or you have your knee tapped by a doctor and your knee jumps, basically what's happened is a long tail of a cell in your brain is sending a signal from your knee to your brain and causing muscle contraction, right? So these are like telephone lines or fiber optic cables for computer packet switching, right? A lot of the computer industry is actually built on things we've discovered about the brain. So here's the 3 type cells. Motor neurons send information from the brain to the body, and sensory neurons send information from the body to the brain. And it turns out certain kinds of nerves have a predominance in the direction they send information, right? And we'll talk about that and why that's important. And then these 2 neurons, sensory and motor neurons, these are excitatory neurons. They basically send signals to cause action potentials to propagate, right? Interneurons are mostly found in the brain. Some are found in the body, but mostly in the brain. They connect neurons to neurons, and their function is primarily inhibitory. They keep nerve cells from firing. So when you saw that little 4-minute video and you saw that action potential propagating, the reason it was propagating was because there were no interneurons inhibiting the flow of that electrical energy. Does that make sense?
Yeah.
So, yeah. So here's another piece that's really fascinating to me, and it's a really interesting way to think about the brain. And that is, each of these 86 billion neurons, if you click it again, you'll see a package of organic sugar. If you take a grain of sugar and you look at a piece of brain tissue, the size of that grain of sugar, what it contains is roughly 100,000 neurons making 1 billion connections, depending on where it's taken from. And so what's amazing to me is, how can we even learn anything about something so complex and so small? Right? It's astonishing. I mean, it's just mind-blowing to me. But here's the other piece. Those 86 billion neurons, basically what each of them is a little battery, right? And what turns the battery on, what propagates an action potential is things that happen in our internal or our external environment. Our internal environment act as the switch, the trigger, and turn the light and the battery on. All right? So imagine 86 billion batteries that you have access to, and as we'll discover later on, we only have conscious access to only about 1% of our capacity, our neural awareness, our sensory awareness. So just imagine if you could double that, right? Just imagine if your kids could double that, right?
Yeah.
Yeah, your job would be
Amazing.
so easy.
Yeah.
Well, there are some
So
programs.
there comes the next question: How are we going to do that?
Well, that's it. I was going to tell you there are some programs around the country that are beginning to figure that out, and we'll talk about a few of those down the road. Okay, so number 7. What's the difference between a neuron and a nerve? So I really didn't know this. I mean, I had to actually research this. But basically, if you click on the screen, you'll see an image that shows a collection of axons wrapped around this covering, this epineurium, and so what a nerve is a collection of long tails, axons, extending out from cells in the brain. So they're basically like long electrical or telephone cables that go throughout your whole body. Right? It's this vast, if you click again, you'll see the autonomic nervous system. And you'll see how the brain sends out these, the brain sends out these fibers, these coaxial cables, and they connect to all our internal body parts. The central nervous system is basically the brain and the spinal cord, and nerves come down through the spinal cord and then extend out through openings and make contact. And then other nerves, cranial nerves, come out that don't go through the spinal cord. They come out and perform a kind of, an important function that we'll talk about when we get to polyvagal theory. So there's this communication process that's happening all the time between our body and our brain. And it turns out that a great way to think about the body is as our unconscious signaling system. The human unconscious lives in the body. And one way we increase our sensory awareness is by becoming aware of how we actually feel in our heart, in our stomach, in our liver. And we can begin to practice paying attention to subtle feelings in these places in our body, and we can learn body language similar to the way we learn a speech language. Right? Does that make sense?
It does. In fact, it's like intuition. If you have a gut reaction to something, or you feel like you should do something, and you're not sure why, but you feel it somatically.
Yeah. If you're paying attention, you can actually...
And on the opposite side, right.
Yeah.
And on the opposite side, if all of a sudden you're feeling very badly about something, if you're listening to that, it might give you pause before you start along that path.
Exactly. Yeah. So our body is this extraordinary receiver and signaling device if we're paying attention to it. And mostly I don't, but I'm learning how important it is. I'm beginning to learn my body's language better and better. And then we click again, the final piece of this slide are the 12 cranial nerves. And we put those in there because those are a big piece of social neuroscience. I mean, we communicate an extraordinary amount of information through the nerves in the head, neck, and face, right? And here they are. And we're going to spend a lot of time on the vagus nerve because that's a big piece of things that go wrong when we have difficulties in the field of social neuroscience. So then finally there's this mnemonic device that neuroscientists like to use for what each of these 12 nerves does, whether they are sensory nerves, motor nerves, or if they perform both function. And the saying is, some say marry money, but my brother says bad business, marry money. So do you get how that works?
Mm-hmm.
So some is
right. So the
S,
olfactory
exactly.
is sensory.
Right.
Mm-hmm.
And then vagus is both, right? Vagus is business. And accessory is marry, and hypoglossal is money. That's just a easy way to remember what each of these nerves are. Okay, so there's another one final image of how the nerves actually operate in the face and head and neck and jaw. So everything we do, like wrinkle our nose, blink our eyes, is all controlled by action potential firing some number of those 86 billion nerves in our brain. There's some interesting research done. There's a great article in the New Yorker called The Naked Face by Malcolm Gladwell. And he talks about research by Paul Ekman, who studied the 43 nerves in the face and began to recognize how our emotional response is displayed by the micro movements of muscles, of the 43 muscles in the face. And he's been really popular with defense and prosecuting attorneys to give courtroom testimony about whether people are lying or not. He had the TV series Lie to Me, based on his research. But it's really interesting because a lot of what gets communicated by the muscles in the face we take in unconsciously. And it ends up being what we would call intuition, right? We just get a sense of someone lying. But if we're actually paying attention, we can come to recognize what it is, that we're actually perceiving below the level of awareness, right?
And children who've experienced trauma are really expert at that.
Absolutely.
They can read someone's face and know what's going to happen because they have to be that way in order to survive.
Right. They have to really have a good acumen for detecting threat.
Mm-hmm.
Now the last animation in this particular slide 7, it's basically how nerves can be damaged, right? Through compression, sheath loss, disconnection, or degeneration. And each of these ways that nerves can be damaged, we are making extraordinary progress in being able to repair. So I'm guessing probably, hopefully, within the remainder of my life, however long that is, we will probably come up with cures for neurodegenerative diseases in the elderly like Parkinson's and Alzheimer's. Because there's so much interest and money being devoted to finding out how these things work. Okay, slide 8. Are everyone's neurons and brains the same? Well, the answer to that question is we all pretty much come in with the same essential structures in place. But then the world goes to work and begins changing things up, begins its own unique wiring process that's more unique than our own fingerprints. And it's constantly doing it shortly after the brain begins to form in utero until we actually take our last breath, and maybe even beyond, right? And at some point, I'll show a video that just shows these neurons operating in real time and how really dynamic and energized and active they are in terms of their looking to make connections and to disconnect and to fire electrical impulses. And so it's like this seething cauldron of activity that's going on all the time inside our skull. And every one of us is unique in that sense. And so when you think about, and this is where the social neuroscience part comes in, when you think about the fact that everyone's brain is uniquely their own, it really makes sense that, and we're moving in this direction, that things like individualized medicine needs to become more prominent in the way we treat people. Individualized education. We each have our own unique interests and learning styles, right? That public education, for the most part, has a really hard time trying to respond to. You can attest to that, right?
Absolutely. And the multiple intelligences with Howard Gardner really tapped into a lot of those learning differences.
Right.
And there was a while that there was a push for that, and schools were starting to look at that, but then, it just becomes education for the large group rather than the individual, because that's what's always been done.
Right.
Charter schools kind of get into that, where they try and do different things, but
Yeah.
public education in general tends to keep doing the same thing.
Right. So as we learn more and more about the brain and how things positively impact it and how things negatively impact it, what we're going to have to do is change a lot of the institutions in the world, basically. And computer technology has a capability of actually addressing some of this in certain ways, in some good ways and some not so good. And we'll see some of that going forward. Yeah, so here's a little heart fingerprint. And then I just wanted to show you actual neurons in the cortex, what they look like under an electron microscope. And these are just, so the cortex is the outer wrapping of the brain. It's like this envelope. And it's about 10 pieces of copy paper thick. And there's 6 layers. And then it's crumpled up and it's stuffed into your skull. That's what all those folds and those hills and valleys are that we typically see in a brain. Right? And so there are certain neurons that only operate at certain levels in the brain, and then certain other ones that extend deeper, and then certain other ones that go from the bottom up, right? And in the cortexes, the gray matter part of the brain is where most of the cognitive functioning happens. And this is what the cells look like. And there's 86 billion of them. 86 billion little batteries. I mean, when you think about it in terms of just a design problem, it's like, holy cow. How do you do that?
How did we get here?
Yeah.
How did we get to that point?
So here's an interesting story that I've told before that, Darwin, you may have heard it, but so I used to be a house builder. And one day I ordered a prefab house that was mostly built in a factory, and it comes out on a couple semis, and there's all wall sections, and there's roof trusses, and there's, foundation parts, and there's floor joists, and It's all in a truck, and it's all stacked up, and it's all got numbered parts. And it's like a giant erector set. And my job is to take them off the truck and put them on the ground, sort them out, and then put them together for an architect's plans, and the end result is a house, right? So one of these came out one day, and it got delivered. And the next morning, I was sitting on atop this pile of house parts, and I was looking at it, and I was thinking, wow, this is pretty amazing. I have the ability to take these parts and assemble them and create a house out of them, right? That afternoon, my daughter was born. And I was in the room when she came out of the womb, and I caught her, and I looked at her, and at that moment, I totally believed in God, because I juxtaposed my ability to build a house, which is so rudimentary, right? Compared to how do you take two cells and build a baby?
Mm-hmm.
It's just astonishing. Okay, what makes neurons and synapses grow? Slide 9. Essentially, what makes them grow well is novelty, an outside world. The brain is basically built to navigate the outside world, to move our bodies through the outside world, through whatever habitat environment we find ourselves in. And its primary function is to process energy and information. And that's a great way to think about the brain, an energy and information processor. Because when you think about it that way, you can begin to readily discern when you're not processing energy and information well. And it's usually when we're under stress, both stress we recognize or stress we don't recognize. If we take an example of children, they are really sponges for learning and will go out and explore the world if they feel safe, right? If they don't feel safe, then they're not able to go out and explore the world. Okay, so that's one of the things that makes neurons and synapses grow. So the next slide, 10, is a sidebar, and I wanted you to just take a look at, we're going to go slowly through these pictures, and the reason I put these in here is because when you just simply looking at these pictures, you feel a certain way in your body, and this is called situated cognition. And this is how the social and physical world makes us feel, right? So the first picture is a field of sunflowers and a sunset. It's quite lovely. Happens here on Whidbey Island a lot. A second is a bucolic scene of a pond with a stone bridge over it. And you just feel this sense of peace and relaxation in your body, right? And then the next slide shows a bunch of tenements built below a bunch of condominiums. And you have a very, very different feeling in your body in response to this environment, right? This is not an environment that's optimal for neural development, nor is the next one, right? So the places we find ourselves in the world profoundly impact what goes on in our brains and in our bodies. I don't know if, I'm assuming people on the call can really feel the difference in these images. And if you were actually standing, embodied out in the middle of this collection of trash, you would, if you were paying attention, you would feel how badly you feel in your body. All right, so that was a sidebar on situated cognition. Now we're going to go to slide 11. Do all living things possess neurons? And the answer to that is all living things that move possess neurons. And I put four four specific things on here because these guys have been really central in neuroscience research. And the reason they've been central is because they're easy to work with, right? So C. elegans is a nematode, a basic worm, has 302 neurons. 302 is a workable number. And we've been able to actually do the whole connectome, the whole map of these 302 neurons, where they connect, what they do, what their function is. And we've been able to do tons and tons and tons of experiments using this simple worm. And then the common housefly, Drosophila melanogaster, is another one. Now we do tons and tons of research and learn and get ideas about how the brain works, and then try to extrapolate findings to human beings. And then a third one, of course, is Radicus norvegicus, who's been the mainstay of scientific laboratory research since time immemorial. Cute little guy. Rat brains and human brains have a lot of structures in common. So we can actually do things to get ideas about how human brains work by experimenting on them. And then the next slide is my favorite. This is the Nobel Prize winning Aplysia californica. And this is astounding to me, but it makes total sense from the years I spent at the Stanford think tank. Eric Kandel spent 30 years working and researching how the two cells in the California sea snail operate. That was all he did. He was searching for memory, and he actually wrote a book called In Search of Memory. And it was through his research with these snails he discovered how memory forms in the brain, how we turn experience, particularly how we turn threatening experiences into memories. And then I included a little poem that his daughter wrote when she was, I think, 8 or 9 years old. Aplysia is like a squishy snail. In rain, in snow, in sleet, in hail. When it is angry, it shoots out ink. The ink is purple. It's not pink. And Aplysia cannot live on land. It doesn't have feet, so it can't stand. It has a very funny mouth, and in winter, it goes to the south. So there's a little girl who really understood and enjoyed her father's work. So those are where much of important brain research has evolved through the years, right? And now, because we have so many developments in imaging technology, we're actually beginning to see live brains in action in the world and discovering things we just never even had an inkling of before. Do some people have more neurons than others? Picture of Gauss's brain. Let's see. So if you look on the left, you'll see Carl Friedrich Gauss's brain, right? And it's apparent to me. It's not apparent to everyone, but it's apparent to me that he's got many more folds and many more valleys and deeper crevices in his brain than who they're describing as a how do they call this person? Oh, a worker, age 57, right? So he was a high-level mathematician. He's the one that invented the bell curve and won a number of prizes for his discoveries in math. And my sense is that because of this is the area that he's worked, of where he worked, and he's constantly, using his brain for in different ways than a manual worker would, he's able to develop many, many, many more connections. And those connections show up as increased hills and valleys. sulci and gyri in his brain. Does that make sense?
It does. It even, when we talk about children coming into school, and many times impoverished families don't have a lot of reading material, so the students come with a lot less words that they know.
Right.
And so you think, well, they have more of these crevices and valleys than the students that are coming in that haven't had all this previous experience and going to museums and, you know, versus staying in their own little area and never leaving.
Yeah.
So
So there's a
more.
wonderful research that took a long time to get out into I don't even think it's out in the mainstream yet necessarily. It's called Meaningful Differences Program. Have you heard of it?
I actually have the book. I don't think I've ever read it, but I have the book.
Yeah. So basically, it was research that looked at, they put voice recorders on children to wear at home, and kids wore them for a period of time, and they came back, and then researchers just simply counted the number of words the children from upper class households heard versus children from poverty households heard. And the difference in the first, in a 3-year period, I think, was something like 8 million more words. Kids just heard many more words. And mostly, a big part of the difference was they heard, kids from poorer households heard discouraging words a lot more than kids in upper income households, right? So they thought, well, basically all we have to do is expose young kids to more positive words. And they did a bunch of experiments. And lo and behold, it made a huge difference in their processing capacity. I mean, they basically increased the brains of these kids, their energy and information processing capacity, some significant percentage. And it makes total sense. Because if you don't use it, you lose it. Slide 13.
Well, wasn't that the premise of the Head Start program?
I'm not familiar with Head Start. I just
Start?
know that it got a lot of mixed reviews, right? But the basic premise is a simple one, and that is the more action potentials you can structure and organize in safe environments for kids, the better the brain grows. Right? Slide 13. Do left and right brains work differently? Well, we've had this conception, that there are significant differences in right and left brains, and to some extent there are, but the important piece here is that the brain is essentially a distributed network with lots of built-in redundancy and duplication, right? There have been amazing findings of people functioning in the world perfectly well with only half a hemisphere. In other words, the left hemisphere was totally missing. So how does that work? Well, essentially the brain works by responding to the environment. And so if you don't have a left hemisphere, then all the functions that you need to operate in the world get crammed into the right, which is pretty astonishing when you think about it. But we'll come to see that there's often an ongoing turf battle in our brains for real estate. So an example would be, there are certain times when windows are open, brain development windows. So like for vision, if your eyes and your brain aren't exposed to light when the vision window's open, you'll essentially not develop the visual cortex in the brain, and it will be taken over by other sensory areas like motor cortex and auditory cortex. It's like, oh, there's some free brain real estate not being used. Let's annex it and use it for our needs, right? And what we're discovering is synesthetes, people who can see numbers in color or feel sounds, or what we're discovering about people like that is they basically have bleed-throughs in neural connections, where one area bleeds through and makes connections into another that aren't normally made in most people. So in a number of these slides, like at the bottom of this one, you'll see research articles that are hyperlinks. And so when you have these PowerPoints in full screen mode, you can simply click on them and they'll take you to the research article that's being referenced, right? And this one's from last month, this year, talking about how, the idea of a left hemisphere and right hemisphere is just really too simplistic. That, left brain thinking, right brain thinking really are just distributed throughout the whole brain. Okay, so let's just try. Slide 14 is pause for questions. Let's just see. I'm going to take everybody off mute. I think I am. Let's see how I do this. Huh. Well, for some reason it's not working. There's somebody I can hear, or it's me. Unfortunately, I can't. It's not working when I click unmute. Well, that's unfortunate. So I just when I was thinking the technology gods were smiling on us, lo and behold, they're not. Darn.
All right. I'm off now.
Oh, yes, you are. Okay. Ruth's there. Oh, she's gone. All right. Well, I'm going to have to work this out, and I apologize. We're going to have to figure out why people don't come off mute when I hit the unmute button. So again, let me just say here that I really want to hear from people, and I'm happy to answer any and all questions. And I'll, if I don't have the answer, I'll either invite both of us to collaborate on researching answers. And you can make appointments to talk to me on the phone between sessions. You can email me anytime, and I'm more than happy to respond. And that includes you, Darlene. Darlene? We lost Darlene. Huh. I see I have you muted. I don't know how to unmute you. I got your... Well, this is frustrating now. Okay, well, I apologize again. Where... I don't even... Oh, huh. All right. Let's see. Let me just try a couple more things here. Nope. All right. Well, I'm going to have to just continue and work with what we have, unfortunately. Huh. All right. Well, I'm assuming you can hear me because I see the microphone going. Darn. That's frustrating. Okay. So now we're going to move through to the next slide, which is 15. And the question is do neurons get born? Do they die? And how? And so here's a slide that shows stem cells, these little blue cells here at the bottom, or in the middle of the slide. And then the green cells are neurons that have the potential to develop into full-blown, mature, functioning little batteries to generate action potentials. But they don't necessarily all come to fruition, right? There are things that happen that either cause them to grow or not. And a lot of the things that cause them to grow or not come out of the environment, right? Emerge out of the social environment, particularly. And so we see here how proteins are the messengers that dictate whether or not these cells will grow. And there are these different groups. Some of them repress growth, like the polycom group proteins, and some of them cause growth to take place. They cause genes to be actively expressed, and that expression ends up causing brain cells to grow. And that's a process called neurogenesis, right? So they're growing, especially in children. They grow throughout our life, but much faster and more of them in childhood. And it's really apparent to see, if you've spent any time around children, that indeed, children are sponges for new learning and new knowledge, right? So that's how they grow. How do they die? We keep clicking through the growth cell. We come to this other slide, good cell death and bad cell death. And this is really important, right? How cells in our bodies and our brain, not only our brain, but our body as well, how they die is really important. And there's two processes that we're going to talk about here. One is apoptosis, which is good cell death. The other is necrosis, which is bad cell death. And what causes and what contributes to these two different ways of cells dying is highly dependent upon the levels of stress in our lives. All right? And so the reason apoptosis is a good way for cells to die is because when they go through the breakdown process, they break down into particles that are, you see them on the right there, they're large enough to actually send a signal to the immune cleanup crew in our body to clean these up and get them out, right? And that's a healthy process, right? We need to have waste management happening in the body all the time in order to end up with a minimal amount of inflammation. Inflammation, bad. No inflammation, good. Necrosis, on the other hand, cells die a different way, and they end up with these small particles on the right, and these aren't sufficiently strong enough to send the signal to the cleanup crew. And so they end up remaining around and causing inflammation, right? The nuclear breakdown of these cells doesn't get cleaned out in efficient ways, and we end up with inflammation. Well, recently, and this is a link too at the bottom, called necrotosis. It's a hybrid that we've discovered, a way that doesn't break cells down to the same size that apoptosis does, but doesn't make them so small that necrosis does. And we're discovering through this process ways to affect immune function by getting cells out of the body. that otherwise would remain behind and be contributing to inflammation. So this is exciting. To me, it's really exciting research, because the whole movement of health in both the world and in research and brain science is toward increasing health and well-being and longer life and happier life. So that's exciting stuff. Slide 17 are a bunch of conditions associated with elevated inflammation. And the top one at the right there is an important one. Inflammation response lowers cognitive ability. So the extent to which we are under stress in our lives measurably impacts our ability to operate in the world using our brain. Inflammation impairs action potential, is one way to think about it. All right? And so those are all these conditions associated with elevated inflammation are hyperlinks, and you can look on them and just see some of the research that shows what happens that's caused by these inflammation processes. Slide 18. It's one of my favorite slides, actually. It's depicting the brain as a distributed parallel processing network, much like a computer. And look how big and beautiful that cerebellum is, isn't it? It's just gorgeous. So this is a really useful way, as I mentioned earlier, to think about the brain, right? It's a distributed network. And its main function is to process energy and information. So when we get tired, like at the end of a day, it's because our energy and information processing capacity has been depleted. We've used it up. It's not an infinite resource. Fortunately, sleep, and good sleep, goes a long way to restoring functionality. And that's the experience of waking up in the morning completely refreshed, right? Now, obviously not everyone wakes up in the morning completely refreshed, in which case, if we begin looking in our lives and thinking about what are some of the things that are impinging upon our capacity for processing energy and information, it begins to become apparent that what some of those things might actually be. And often, it turns out to be some of the relationships in our lives that are causing us undue stress. Okay, so then there's another brain picture on slide 18 that's depicting a circuit board, and I like this one too. Because basically, all these 86 billion batteries in the brain are on-off switches, ones or zeros. Action potentials either fire or they don't. And as we will discover when we look through polyvagal, the session on polyvagal theory, the freeze response turns out to be a failure of information energy processing. And it has significant impact on brain function down the road, especially when it happens to kids early. All right, the good news, next slide. The more energy and information our brain is able to process, the more reliable behaviors we're able to develop and display, especially under stress. And we've listed 5 personality traits that increased energy and information processing moves us in the direction of. And they have these are basically the traits that researchers study when they study personality, right? These 5 areas: extroversion, introversion balance, neuroticism, conscientiousness, agreeableness, and openness. And basically all of these personality traits are measures of our ability to regulate emotion, to regulate our emotional reactivity in the world, to be able to be in relationship with other people and to not be as reactive as we might otherwise be if our brains weren't just processing energy and information, ideally. And obviously these aren't constants, right? In any day we could be on a continuum anywhere on each of these measures, each of these traits. But generally, the more energy and information we can process, the more we're fun to be around. Yeah. All right, slide 19. Coming up on the end here. What happens to the brain's and body's animating energy when death occurs? And this was just a question that, I was curious about if I was taking this class. And I found this quotation that I thought really explained it well. And I think it's actually, it helps my neurophysiology when I think about death. So I'm going to read it because I really like what it says. There's a picture of a hand. We know what happens to the body on death. What happens to the energy and the animating energy of the body is up for lots of discussion, right? Well, here's what physicist has to say about it. You want a physicist to speak at your funeral. You want the physicist to talk to your grieving family about the conservation of energy, so they will understand that your energy has not died. You want the physicist to remind your sobbing mother about the first law of thermodynamics, that no energy gets created in the universe and none is destroyed. You want your mother to know that all your energy, every vibration, every BTU of heat, every wave of every particle that was her beloved child remains with her in this world. And at one point you'd hope that the physicist would step down from the pulpit and walk to your broken-hearted spouse there in the pew and tell him that all the photons that ever bounced off your face, all the particles whose paths were interrupted by your smile, by the touch of your hair, hundreds of trillions of particles, have raced off like children, their ways forever changed by you. And as your widow rocks in the arms of a loving family, may the physicist let her know that all the photons that bounced from you were gathered in the particle detectors at her eyes, that those photons created within her constellations of electromagnetically charged neurons whose energy will go on forever. And you'll want the physicist to explain to those who loved you that they need not have faith. Indeed, they should not have faith. Let them know that they can measure, that scientists have measured precisely the conservation of energy and found it accurate, verifiable, and consistent across space and time. You can hope your family will examine the evidence and satisfy themselves that the science is sound and that they'll be comforted to know your energy's still around. According to the law of conservation of energy, not a bit of you is gone. You're just less orderly. Amen. So there we have this first session. And again, I encourage people to be in touch with me, and I'll get this mute situation straightened out for next session for sure. And then at the end of each session, I'm going to offer you 3 resources for further explanation. works that I have found to be particularly meaningful for me in my understanding of this material. So the first one is Antonio Damasio's The Feeling of What Happens, Body and Emotion, Making of Consciousness. And he's a research scientist at USC, and he's just a really wonderful writer. That's partly why I like a lot of these authors, for their writing style and their ability to communicate complex information in simple language. And the second one is Moab Kostandi's recent book. It actually was published this month, I think. 50 Ideas You Really Need to Know About the Human Brain. And this is basically a book that strips out all the hype and publishing, commercial publishing interpretations of research findings, and really tells you what we actually know specifically for sure about the human brain. And it's a 50 ideas series, so each idea, it's a 200-page book, each idea is only 4 pages. And it's easy to get through, and you actually see where the state of brain research currently is in the world. And then finally, Brain Facts. If you put your cursor on this one while you're in full screen view, you'll see that this is actually a link that will take you to the primer on brain and nervous system facts on the internet. So here we are. We're at the end. How do we do? An hour and a half, but we didn't have time for questions, which is really frustrating. Anyway, I will work out this, and again, I apologize for the technology snafu, and I will look forward to hearing from you in any way you'd like to be in touch. So thank you very much, and have a great evening. Bye for now.